how many people in this room believe that the sun goes around the Earth as opposed to the Earth going around the sun? How many people here believe that the sun goes around the Earth? You weren't listening yet, right? That's okay. I would have been the guy in the back. Yeah, I believe it. But the question is, right, if I go outside in the morning, here comes the sun, right? It's coming up. In the afternoon, it's here. And at nighttime, it's there. And if I call my friend, in China, he'll say, oh, yeah, now I can see it. So I'm like, oh, I know exactly what's going on. The Earth is round, and the sun's going around it. I've got evidence of that. I've just called my friend in China. He says it's over there now. I knew it was here before, so it's going around. It looks like it's going around. It looks like the sun's going around it. So how do we know? So how do you know that the Earth is actually going around the sun? Because within the model that we currently have, right, it's really what's going on is the Earth is spinning. The sun is basically staying there, and the Earth is spinning around every 24 hours. Yeah?
Because Venus is always near the horizon of the sun, and you can never see all the phases of Venus.
Okay, but I haven't talked about Venus. What does Venus have to do with this? I'm just saying that in the morning, the sun is here, the sun goes up, and then it comes down. It looks to me like the sun is going around. Now, I know where you're going. Okay? So let me just continue with this line a little bit more. Yeah?
Seasons?
Seasons. Okay, well, what does seasons have to do with whether they're not...
When it comes to the sun,
So what's happening here is, what I'm trying to do is I'm trying to push your belief system a little bit. I'm trying to push you guys to try to justify why you believe the universe is the way it is. And a lot of us are this way, and I'm not trying to pick on you because I also fall into the same thing. Like, I believe that because everybody told me that was true. Okay? This is why people, 3,000 years ago, this is why there were people who believed the Earth was flat. Because everyone told me the Earth was flat, it looked like it was flat, let's stop worrying about it. Move on with my life. Okay? Same thing with the Earth going around the sun. Most people a long time ago, in fact, very intelligent people believed that the sun was going around the Earth. And it's much, much harder to figure out that the sun is going around, that the Earth is going around the sun than it is to figure out it's round, it turns out. It's a very tricky argument to figure this out when you're landlocked. That is, when you're locked to the planet and you can't just fly a spaceship out and figure out what's going on. So that's what I'm going to talk about today. I'm going to talk about the sort of gradual buildup of this picture that we have about what the universe looks like, and some of the implications that are immediately thrust upon you when you accept this idea. This very simple idea that the Earth is going around the sun. It turns out that that has very big implications for lots of things. And it's not just this idea that the Earth isn't the center of the universe anymore. Okay, that's an idea that probably a lot of you have heard before, that there's this Copernican revolution. Suddenly we realize we're not the center of the universe, and there's all of this sort of, ramifications of this that are supposed to affect our psyche about how important we are. But there are other things that are sort of immediately obvious once you accept this idea that the Earth is going around the sun. So that's what I'm going to talk about today, stuff like this. So this is, Homer's view of the universe, the very ancient Greek picture of the universe, and it was sort of like a snow globe universe. Okay, there's this flat land, and then there's the dome of the sky up above. And this is what it looks like, right? You go out in the desert and you look around, it looks like you're in a big snow globe. Okay. But this picture was overturned even among the ancient Greeks by a series of sort of empirical arguments. So what I wanted to do now is sort of introduce what Carl Sagan calls the pre-Socratic philosophers. And this sort of origin of empirical belief systems, specifically, this is sort of the dawning of the scientific method. It wasn't really thought of in that way. You could probably characterize this as sort of the dawning of the scientific method. And Sagan is just a master at talking about this stuff. So I thought what I would do, rather than try to emulate him, is just show him. So this is just a little video from YouTube, and I've linked this in lots of places. I want to just show it very quickly.
Of all the ancient scientists, it is he who speaks most clearly to us across. Of all the ancient scientists, it is he who speaks most clearly.
I'm sorry, wrong one.
This great revolution happened between 600 and 400 BC. It was accomplished by the same practical and productive people who made the society function. Political power was in the hands of the merchants, who promoted the technology on which their prosperity depended. The earliest pioneers of science were merchants and artisans and their children. The first Ionian scientist was named Thales. He was born over there in the city of Miletus across this narrow strait. He had traveled in Egypt and was conversant with knowledge of Babylon. Like the Babylonians, he believed that the world had once all been water. To explain the dry land, the Babylonians added that their god Marduk had placed a mat on the face of the waters and piled dirt on top of it. Thales had a similar view, but he left Marduk out. Yes, the world had once been mostly water, but it was a natural process which explained the dry land. Thales thought it was similar to the silting up he had observed at the delta of the river Nile. Whether Thales' conclusions were right or wrong is not nearly as important as his approach. The world was not made by the gods, but instead was the result of material forces interacting in nature. Thales brought back from Babylon and Egypt the seeds of new sciences, astronomy and geometry, sciences which would sprout and grow in the fertile soil of Ionia. Anaximander of Miletus, over there, was a friend and colleague of Thales, one of the first people that we know of to have actually done an experiment. By examining the moving shadow cast by a vertical stick, he determined accurately the length of the year and the length of the seasons. For ages, men had used sticks to club and spear each other. Anaximander used a stick to measure time. The tools and techniques they developed, which remain the basis of modern technology. This was the time of Theodorus, the master engineer of the age, a man who is credited with the invention of the key, the ruler, the carpenter's square, the level, the lathe, the bronze casting. Why are there no monuments to this man? Those who dreamt and speculated and deduced about the laws of nature talked to the engineers and the technologists. They were often the same people. The practical and the theoretical were one. This new hybrid of abstract thought and everyday experience blossomed into science. When these practical men turned their attention to the natural world, they began to uncover hidden wonders and breathtaking possibilities. Anaximander studied the profusion of living things and saw their interrelationships. He concluded that life had originated in water and mud, and then colonized the dry land. Human beings, he said, must have evolved from simpler forms. This insight had to wait 24 centuries until its truth was demonstrated by Charles Darwin. Nothing was excluded from the investigations of these first scientists. Even the air became the subject of close examination by a Greek from Sicily named Empedocles. He made an astonishing discovery with a household implement that people had used for centuries. This is the so-called water thief. It's a brazen sphere with a neck and a hole at the top, and a set of little holes at the bottom. It was used as a kitchen ladle. You fill it by immersing it in water. If, after it's been in there a little bit, you pull it out with the neck uncovered, then the water trickles out the little holes, making a small shower. Instead, if you pull it out with the neck covered, the water is retained. Now, try to fill it with the neck covered with my thumb. Nothing happens. Why not? There's something in the way. Some material is blocking the access of the water into the sphere. I can't see any such material. What could it be? Empedocles identified it as air. What else could it be? A thing you can't see can exert pressure, can frustrate my wish to fill this vessel with water if I were dumb enough to leave my thumb on the neck. Empedocles had discovered the invisible. Air, he thought, must be matter in a form so finely divided it couldn't be seen. This hint, this whiff of the existence of atoms was carried much further by a contemporary named Democritus.
There's a little bit more of this that I'll play, and then I'll stop.
Of all the ancient scientists, it is he who speaks most clearly to us across the centuries. The few surviving fragments of his scientific writings reveal a mind of the highest logical and intuitive powers. He believed that a large number of other worlds wander through space, that worlds are born and die, that some are rich in living creatures and others are dry and barren. He was the first to understand that the Milky Way is an aggregate of the light of innumerable faint stars, beyond campfires in the sky, beyond the milk of Hera, beyond the backbone of night. The mind of Democritus soared. He saw deep connections between the heavens and the earth. Man, he said, is a microcosm, a little cosmos. Democritus came from the Ionian town of Abdera on the northern Aegean shore. In those days, Abdera was the butt of jokes. If around the year 400 BC, in the equivalent of a little outdoor restaurant like this, you told a story about someone from Abdera, you were guaranteed a laugh. It was, in a way, the Brooklyn of its time. For Democritus, all of life was to be enjoyed and understood. In fact, for him, understanding and enjoyment were pretty much the same thing. He said, a life without festivity is a long road without an inn. Democritus may have come from Abdera, but he was no dummy. Democritus understood that the complex forms, changes, and motions of the material world all derived from the interaction of very simple moving parts. He called these parts atoms. All material objects are collections of atoms intricately assembled, even we. When I cut this apple, the knife must be passing through empty spaces between the atoms, Democritus argued. If there were no such empty spaces, no void, then the knife would encounter some impenetrable atom, and the apple wouldn't be cut. Let's compare the cross-sections of the two. Are the exposed areas exactly equal? No, said Democritus. The curvature of the apple forces this slice to be slightly shorter than the rest of the apple. If they were equally tall, then we'd have a cylinder and not an apple. No matter how sharp the knife, these two pieces have unequal cross-sections. But why? Because on the scale of the very small, matter exhibits some irreducible roughness. And this fine scale of roughness Democritus of Abdera identified with the world of the atoms. His arguments are not those we use today, but they're elegant and subtle and derived from everyday experience. And his conclusions were fundamentally right.
Okay. So first, I hope you guys found that interesting. I mean, I hope it wasn't like just me making you watch a movie for an hour. But I think Sagan does a really good job of just emphasizing how amazing it was that some people, sort of empirically minded people living thousands of years ago, were able to begin to deduce these things that we now sort of have empirical evidence that's true. Now, that's just one step of the scientific method, having an idea based on things that you observe that's consistent with what you see. But the real power of the scientific method is to continue to subject those ideas to data, to experiments, to observation, to see if they are really true, to come up with ways of testing these ideas and either ruling them out or allowing these ideas to live on. So this idea that all matter is made up of atoms has been around a very long time. Okay, so this is Democritus, I think thousands of years ago, having this idea. But the acceptance of atoms, that atoms really existed, that there really were even molecules that make up, solids, this was really not set in stone or fully confirmed by modern science until the 20th century. In the very beginning of the 20th century was it really solidified. I mean, this was a question that actually Einstein worked on as part of his PhD thesis. So just because people have good ideas, it doesn't mean that those ideas are correct. But it's sort of this chain of arguments that you have to build up. So the first picture, the first sort of semi-scientific picture of the universe itself was one that was put forth by Aristotle. And in Aristotle's model, the Earth is spherical. Okay? And he had several reasons to believe that the Earth was actually spherical and not flat, like in the Homer model. And there are a couple different things. So one of them, which I've listed here as number 3, is something that was mentioned earlier. That, let's say you stand on the horizon and you watch a sailboat sail off into the distance. What you'll notice is that you'll see the bottom part of the sailboat start to disappear, but the mast and the very tip of the sail, you'll see that for much longer than you'll see the rest of the sailboat. So it's as if it's going over a very slow horizon and just the mast is sticking up above the horizon, and then finally it falls off. So his argument is there must be some curvature to the land, and you stop seeing the ship as it goes down that, it's sort of this big curve. And the curve itself is what blocks you from seeing the rest of the ship as it sails away on a very clear day. He had a few other reasons for believing this as well. So another thing was during a lunar eclipse. So what happens in a lunar eclipse is that the Earth gets in the way of the sun. So the sun is casting light on the moon, and that's why the moon is lit up at night. Okay? But if the Earth gets in the way of the sun, it blocks some of the light, and you see a shadow cast on the moon. And the ancient Greeks understood that. They understood that that's what was going on during a lunar eclipse. And the shadow that was cast by the Earth is always looks like a circle. And the only thing that can cast a shadow that's always a circle, no matter how you turn it around, is a ball. Okay, so if you hold a tennis ball up and you shine a light on it, it will cast a shadow that looks like a circle on the wall. And it doesn't matter how I turn that tennis ball around, it's always a circle. So that was another reason why he argued that the Earth was a sphere. The final thing that he said was that if I look up in the sky, I can see certain constellations. Okay? So let's say at a certain time of night, I look and I see the very bottom of Orion. Okay? It has some shape, some stars, and some configuration. It's very recognizable on a clear night. And let's say Orion's very low on the sky. So if I travel in one direction away from that, the Earth curves, and suddenly my view of that part of the sky is blocked. I can't see that horizon. I can't see that constellation anymore. And that's true. As you travel, say, from north to south on the Earth, there are certain constellations that you can no longer see. Because, in fact, the argument is they're blocked by the bulge of the Earth. And at the same time, now you're on this Earth that's curved. You walk down to this side of the Earth, and suddenly you can see new constellations on this part of the sky that in the past were covered up. So by making these arguments, he was able to build up sort of an empirical database that suggested to him that the Earth was in fact spherical. And even though it appeared to be flat, it wasn't perfectly flat. It was just very, very big. So if it's very, very big and the curvature is very small, it seems locally flat. And that's basically what the Earth is. Does that make sense? So you can see that this is a pretty clever thing. I mean, Aristotle was not dumb, right? It's not that easy to come up with ideas right off the top of your head about why we believe the Earth is spherical even today. I actually was really impressed with the guy in the back who said, "Oh, I've seen a picture from space." Okay, that's a great empirical argument for why we know the Earth is spherical. A lot of times when I teach this course, people don't come up with that answer very quickly. Okay, so we have a lot of advantages. And this is just to emphasize, it is quite interesting that Aristotle knew this and figured this out. But the other thing I also wanted to mention is, during the Middle Ages, okay, Aristotle was considered the ultimate authority. And most educated people, at least in the Christian and Muslim worlds who were aware of Aristotle's work, knew that the Earth was round. And as I mentioned before, in the Divine Comedy, which was written around 1300 AD, there's mention of the Earth being spherical. Now, Aristotle didn't stop with just the Earth. Aristotle also had a picture of sort of what he regarded as the entire universe. And this is a cosmological model. And in his model of cosmology, the Earth, this sphere, sat at the center of everything. And all the planets and the sun all orbited around the Earth. Okay? Now, the other thing that was kind of interesting and kind of embedded in this model, and almost sort of part of the, the way people saw themselves at this time, is that the Earth was the Earth was corruptible, and the heavens were perfect. Okay? So the Earth had decay, and people could die, and there was sin, and all kinds of stuff like that. I mean, Aristotle didn't use the word sin, but it was kind of that idea. And the heavens were perfect and incorruptible. So all the objects in the heavens were perfect spheres. Everything traveled on what people considered to be perfect shapes, like circles. Circles and spheres were kind of considered perfect things, and everything was a sphere or traveled in a circle and that kind of thing. And all the planets and the sun itself all traveled around the Earth on these celestial spheres that were kind of these fixed spheres that rotated around the Earth. And that was the model. So I mentioned this before, that the ancient Greek philosophers believed that circles and spheres were perfect shapes. And to them, therefore, it seemed appropriate that the Earth was a sphere, all the heavenly bodies were spheres, and everything orbited around us in spheres. And that's one of the things that was motivated by Greek mathematicians to develop these ideas. Now, another thing I wanted to mention, just sort of while we're talking about the ancient Greeks, I'll get back to why I'm talking about this later, is that, these first mathematicians were interested in lots of different things. They were interested in beauty that you could derive from geometry in lots of different ways. And one of the shapes that they studied besides the sphere and besides the circle was an ellipse. So people have heard of ellipses. Okay? If you remember from your geometry classes in high school, there's lots of different ways of defining ellipses. One simple way of thinking about what an ellipse is if you take two thumbtacks and you tack them down to a table, and you tie a string to one thumbtack and another string, the other end of the string to the other thumbtack, and put a pencil at the edge of the string, and you draw a shape around it. That shape that you draw is an ellipse. And you can define that mathematically. Okay? Specifically, an ellipse has two foci, and the two foci are those thumbtacks. And A plus B, which is the length of the string. Okay, so when you pull it taut in one direction, that's the edge of the ellipse. And when you pull it taut over here, you can see that you have the same string, so A plus B is always the same. And that's how you define an ellipse. A circle is an ellipse where both the thumbtacks are in the same place. And then you just have one string that's going around like that with a radius. So they studied this thing because of its mathematical beauty. This is the thing I was trying to describe with the pencil and the thumbtacks. That's what it is. Okay. Now, I'm bringing this up now because I'm going to talk about it later. All right? An ellipse is an interesting mathematical geometrical shape that the Greek mathematicians studied for no other reason that it was sort of had a certain elegance in a geometrical sense. What eventually Kepler would show is that the planets actually travel around the sun on ellipses. The shapes of their orbits are perfect ellipses. And that is true today. We know that the planets travel around the sun on ellipses. And what's interesting is, even though the Greeks didn't realize it, they had already talked about the ellipse and studied its properties long ago, before anyone realized that the planets behave that way. And you see that a lot in science, that mathematicians will study certain things like equations and shapes and properties that they've derived because they have a certain beauty, a certain mathematical beauty, and then later on it will be realized that nature actually uses those shapes or equations or whatever in practice. That for some reason the universe seems to realize this beauty in actuality. Now, there was a problem with Aristotle's model when it was actually subjected to real data. And it wasn't a huge problem, but the Greeks knew about it, and they cared about this because they wanted to know where the planets were in the sky at different times of the year. Part of the reason for this is, if you were an astronomer, you probably made your living as an astrologer. Okay, and especially kings wanted to know where the planets were in the sky, because they had this idea that affected what the outcomes of battles would be, and they wanted to use this to base things on. And people also wanted to be able to use the planets to tell them, when they should plant crops and this kind of thing as well. So there was a lot of sort of practical reasons why astronomers wanted to be able to predict and know exactly where the planets were going to appear in the sky from one day to the next. Now, one of the things that people realized for a very long time, and maybe many of you know this as well, I mean, you can observe this yourself, is that if you watch, for example, Mars on the sky from one day to the next at the same time of night, it will sort of appear here in the sky, and then later on it will move. So, Mars sort of tracks across the sky with time. And it does something funny. It doesn't just go in one direction. It tends to backtrack. So this is what it looks like in February, March, April, and then in June it went back, and then it will keep going forward again. Okay. So this is called retrograde motion. It means going backwards. So the planets will do this kind of thing, jig-jag in the sky. And it's really hard to come up with a model where if all the planets are just orbiting around the Earth on a celestial sphere, how this could possibly be happening. Because if they're just going in one direction and the Earth is sitting in the middle, they got no business backing up. So the question was, what's going on? And right, so Aristotle's model didn't explain this. And so this was actually the first crack. You could say, okay, we should have known there was something up with Aristotle's theory, because it didn't really work. There were certain things it couldn't explain. Now, about 140 AD, this famous astronomer of antiquity named Ptolemy, who was in Alexandria, developed a model that was based on Aristotle's model, but sort of changed it a little bit, that perfectly predicted exactly where the planets were going to be. And the picture he had is a little bit funny, but this is what it was. Okay, so imagine you've got a planet that's going around the Earth. This was their picture, right? What Ptolemy said is that, well, actually what's going on is the planet is not going around in a perfect circle, but the planet itself is on a little orbit that goes in a circle, and it's orbiting around a point that's going around the Earth in a circle. So it's like a circle on top of a circle. Because remember, they were all about circles. They like spheres and circles. So it's like if somehow make the universe work as a combination of spheres and circles, then, that's how it ought to go. That was just the picture they had. And so the idea was you have this kind of loop-de-loop. Planets were going on little loop-de-loops around the Earth. This is the Ptolemaic model. And so the thing about this is this explains retrograde motion. That if you're sitting here on Earth and you're watching a planet go along, okay, the planet's doing a loop-de-loop, and for a while it'll look like it's all going in the same direction across the sky, but at a certain point in the loop-de-loop, you see it flip backwards and go forward again. And that's why it looks like, according to Ptolemy, this is why it does that retrograde motion. Carefully arranging how big this circle was and how big this circle was, he can make his model match everything. And what was interesting about this model is that you actually were able to predict things. So the next time of year, it was worked out, so it basically got the right answer. And that's why people used it. They used it because it worked. Okay, and in fact, this model was the accepted picture of the universe, at least in the Western world, for 1,400 years. This is the longest lasting cosmological model in a scientific sense that's ever existed. Okay? Now, I think it's fair to say that this is pretty crazy. This looks insane. If someone came to you and they said, look, I have a new idea about how the universe works. All the planets orbit on circles, and they're on top of other circles, and when I do this, things start to work. Okay. But, it worked, and there was no way for anyone to say it didn't work. It's unclear if everybody really regarded this as really what the universe was doing, or if they just said, well, this is a tool that I use so I know where the planets are in the sky, so that then I can plan my wars, or whatever. So a long time later, much later, Nicholas Copernicus was addressing the question of the planets and the sun and the solar system. And he proposed a somewhat different model. Now, another thing that sort of happened in there that I haven't really spent much time mentioning is around this time, a lot of the more ancient texts from the ancient Greek philosophers that didn't necessarily agree with everything Aristotle said started to come to light. And a lot of the scholars in Europe who, sort of in the past, they had been taught that basically Aristotle is right, he is the authority on all, so don't question Aristotle, okay? Started to realize, wait, there were contemporaries of Aristotle, even people who lived before Aristotle, who didn't necessarily believe everything he said, and had other ideas. And this began to make people question a little bit, well, maybe there's something else going on. So Copernicus, for example, said, I think this whole circles on circles model is silly. I think it's more elegant and somewhat more beautiful if I arrange the planets in the sun this way, put the sun in the center and have all the planets going around the sun. I think that's a much simpler model, and what's more, it actually explains everything. So within this picture, the reason why the sun comes up and goes down is not because the sun's going around, but because the Earth is spinning, which had its own sort of problems. People themselves said, well, that's crazy. Clearly, the Earth's not spinning. But Copernicus sort of put forth this idea because he just thought it was a more elegant solution. And really, there was no way. This model was equally as good at explaining the data as Ptolemy's, more or less. And so it also explained retrograde motion. Because basically what's going on is the Earth's going around the sun a bit faster than the outer planet. So you can explain the retrograde motion as, I haven't passed it yet, now I've passed it, so it sort of looks on the sky like it's going backwards and forwards. You can see that from this diagram a little bit here. Okay, so this dot is supposed to be how it's projected on the sky from the Earth. So it sort of stops and then goes forward again. Are there questions about this? So still, at the same time, there is no way to really tell the difference between these models. And in fact, there's a lot of kind of common sense arguments that you could make that says, well, there's no way this is happening. So what kind of common sense arguments might you make? Yeah. I don't feel it's moving, first of all. So you're telling me that the Earth is moving around the sun really fast? I don't feel that. And you're also telling me the Earth is spinning around on its axis really fast, too? I don't feel that either. So that's crazy, right? So what's crazier? The idea that the Earth is spinning around on its axis every 24 hours, and also zooming around the sun at some incredible speed, much faster than our horses can travel. Or that all the planets are just going around in circles on circles. So in terms of just kind of a plausibility argument, it's unclear which is crazier. In fact, you might argue that the fact that the Earth is moving is crazier. It's very difficult to imagine that that's really what's going on, right? So I'm going to need some proof. I'm going to need some pretty extraordinary proof to show that this one model is better than the other model. And that's what people started to do. Now, Copernicus was not the first person to suggest that the Earth goes around the sun. Okay? So 18 centuries earlier, this guy named Aristarchus argued that to him it would make more sense that the Earth was going around the sun. And let me explain roughly why he said this. So one of the things that Aristarchus did is he figured out how to measure the distances to the sun and distance to the moon. And he figured out that the sun was way, way, way bigger than the Earth and way bigger than the moon. And he did this using geometry. Okay? And basically using triangles. So a good rule of thumb is anything that you can figure out using triangles and geometry, the Greeks did it because they were really good at geometry. Okay, so anything that you could probably ever do doing geometry, basic geometry, there's some ancient Greek person who did it 3,000 years ago. Okay, and this was one of these things. So it turns out, if you're really good at trigonometry, and I'll explain this in a future lecture exactly what he did, he was able to figure out that the sun was much, much, much bigger than the moon. Okay. And so for him, it was obvious then that since the sun is so much bigger than the Earth and the moon, that the big thing should not be going around the little thing, but the little thing ought to be going around the big thing. That was basically his argument. Okay, and he suggested that this was true. And in fact, Copernicus referenced Aristarchus in his first draft of his book on the heavens. Yeah.
What did they say the moon did? They say that the moon went around the Earth?
Yeah, everyone thought that the moon went around the Earth. So that was, both sides agree on that. And we still believe the moon goes around the Earth. So but Aristotle was cool with that because he liked stuff going around the Earth. Well, one of the things about the moon, so I'm glad you asked about the moon. I'll mention anyway. So one of the things about the moon that Aristotle would observe the moon and show that it wasn't perfect. And that was one of the cracks in the armor of the Aristotle models. Remember I mentioned the idea that everything in the heavens is perfect. And Earth is the one Earth is messed up. Okay? There's all kinds of decay and bad stuff all sunk through the Earth. Everything in the heavens is perfect. What Galileo did is using a telescope, which was a big deal here. He was the first person to point a telescope at the sky. He saw that the moon had mountains and craters and stuff, which meant it wasn't a perfect sphere. And so, okay, that was wrong. Aristotle was wrong about that. And it was sort of like a domino effect. That, well, if he's wrong about that, he could be wrong about other stuff. Now, one of the reasons why people didn't accept this Aristarchus model is for the same thing we've been talking about. It's crazy to think the Earth is moving this way. And there's a very interesting, another sort of removal just from, but maybe you don't feel it, maybe you do feel it if the Earth is moving, but there's something else that this implies, okay? So imagine that we're on the Earth and it's going around the sun, all right? And this is much like, for example, being on a merry-go-round, all right? The sun is the center of the merry-go-round, and I'm on the merry-go-round, and I'm going around, the merry-go-round. Okay, so 6 months later, I'm on this side of the merry-go-round, and then 6 months later, I'm on this side. All right? So if I'm up here going around in a circle, and I'm looking out at you people, okay? Let's say I pick my favorite person, Cincinnati Reds, okay? So here's my favorite person. I'm watching you as I go around the sun. Now look at what I have to do to my finger as I point to this guy. I got to move it, right? If you're on a merry-go-round and you're looking at your friend who's out watching you, you've got to constantly be turning your head to see him. Okay? Right? Because you're moving and that person's staying still. Or another way to think about it is if you're on a train and the train is just moving in one direction and you're looking at buildings going by, you've got to turn your head because they shift. The angular position of them relative to your head is shifting all the time because you're moving. Right? The same thing should be true with the stars. So the stars are out there. Okay, we see them in these points of light. And if the Earth is going around the sun, you would expect that the positions of the stars in the sky, one time of the year I'm here, if I wait 6 months, now I'm over here. If I'm looking at the same star, I'm putting my finger at it now, and as I go to the other side of the sun, I have to shift my point. I have to move my arm by a certain angle. Okay? So there's an angular shift in the positions of the stars from one time of the year to the next. So if I were just standing here and the Earth was moving, if I'm pointing at a star, my arm has to do this, track it. That's what you would think. Does that make sense? Are people good with this? But that's never seen, okay? The ancient Greeks could never, ever see the stars shift at all in their positions in the sky relative to where the Earth was supposed to be around the sun. They didn't move at all. They just stayed right there. Okay? So what I'm trying to say here is here's the star you're looking at. From one time of the year to the next, the projected position of that star ought to shift on the sky. Now, what's seen is that it doesn't shift, at least up to the angle by which you can measure with your eye. It doesn't move at all. And so what that means is that the stars have to be very far away compared to the distance between the Earth and the sun. Okay? So if you were on a train and you were doing this analogy, it would be like looking at a distant mountain peak. So if you're on a train going by and you look at a very distant mountain peak, you don't have to turn your head and do this, right? It just stays there. That's because it's so far away. It's only the stuff that's nearby that you have to turn your head like this, right? So that's what this means. So the upshot is that once you accept the idea that the Earth is going around the sun, it immediately implies that the universe itself is much, much, much bigger than anyone thought possible. Okay? So the people in the past dismissed this idea because it's impossible that the stars are that far away. That would mean they're just so much farther away than the distance between the Earth and the sun, and the distance between the Earth and the sun is huge. So by accepting this model, if you were to like this model better than Aristotle's or Ptolemy's model, you're immediately buying into the idea that the universe is unimaginably big. And of course, now we know that this is what's going on, and the stars are very, very far away. The universe is so weird that people really couldn't imagine it to be that weird in the past. Even these great thinkers like Aristotle, who were extremely imaginative. Okay? who were always thinking outside of the box and coming up with new ideas. Just couldn't fathom that the universe could possibly be that big. And that was one of the ideas. They rejected this idea as out of hand. So these are some important questions, right? We'd like to know, what's the universe like that we're living in? How big is this universe? All of this kind of stuff. And so there was a march towards trying to understand it. Another important figure in this sort of historical timeline was Tycho Brahe, who was a Danish astronomer. And one of the things that he did is he really raised the bar on very precise measurements of the planets. So the telescope was not quite yet invented, but what he did is he had complicated instruments that he used to sort of line up, points in the sky and that were, set up to mechanical devices where he could measure angles to stars very accurately and angles to planets very accurately. And with this, he just created incredibly detailed books, lists of where planets were, at what time of night, and what day, and sort of tracked out the positions of all the planets on the sky very, very, very accurately. And then Kepler, who eventually came to work with Brahe, and analyze his data and try to put it into some kind of mathematical context. Kepler was really a great mathematician. Brahe was really the observer. And Kepler came in later as his assistant and eventually took over and started analyzing his data. Tycho was not a fan of Copernicus. He didn't really like this model. But Kepler, somewhat younger, thought this was an interesting idea, especially when he began to realize that it was very difficult for him to come up with a Ptolemaic system that matched the great observational detail of all this data set of where the planets were. Very precise maps. It's very difficult for him to do. What he realized is the only way for him to actually characterize where the planets were in the sky and what they were doing is if they were orbiting the sun not on perfect circles, as Copernicus had suggested, but instead were orbiting around in these ellipses. And recall, these ellipses were things that had been known by mathematicians for centuries. The sun actually sits at one of the foci of the ellipse, and all the planets go around like this. I should mention that this is a little bit exaggerated. The orbit of the Earth is much closer to a circle than this. Now, based on these observations, he was able to deduce 3 laws of planetary motion, which I'll talk about later, one of which was that planets orbit the sun on ellipses. The final person in this story, really kind of the end, well, an important ending to this story comes for Galileo. Okay, so Galileo, Galilei was a scientist. A lot of people argue the first really modern scientist who flourished in Italy. Around the same time when Copernicus was advocating his theory, sort of a contemporary of Kepler. In fact, interestingly enough, Kepler was sort of jealous of all the attention that Galileo eventually got. Sort of interesting rivalry there, but whatever. The thing that Galileo did that was new, that really allowed him to kind of stand out, was that he had better tools than anybody else had had in the past. He had a telescope. The telescope was invented about the same time somewhere else in Europe. And Galileo heard about it. And the reason why the telescope was invented, obviously, is because you want to keep a lookout for people coming, like when the merchants are coming in with their stuff, you want to sight them first, or maybe you want to use them if you're on a ship so you can sight dry land fast. That's kind of why it was invented. The great optics, people were beginning to experiment with the science of optics. So Galileo heard that someone had invented this telescope and had heard roughly how it worked, so he just built his own, which is impressive. And this is a model of what his telescope looked like. It was about as powerful as like a cheap pair of binoculars that you could buy now at Target or something. But what he did, he was the first person to point it up at the sky and look at stuff. And by doing this, he really change the way we see the universe. So as I mentioned, one of the first things he did is he looked at the moon. That's the first thing you would, the most obvious thing to look at with your binoculars is the moon. If you do that, you see that the moon is not perfect. The moon has got mountains and craters and all kinds of stuff on it, which immediately implies that at least Aristotle was wrong about something. Not all heavenly objects are perfect spheres. Another thing he did is he discovered that there are these little things that always appear in the sky next to Jupiter. And in fact, if you watch Jupiter night after night after night, these little things look like they're going around Jupiter. And what he did, therefore, is he discovered that Jupiter has its own moons. So there were 4 moons that Galileo was able to see, and those 4 moons are called the Galilean moons of Jupiter now. But another implication of this is that not everything orbits the Earth. So you can see with this telescope that not everything is going around the Earth. At least some things are going around other planets. And again, as soon as you start to admit to the idea that, well, not everything's going around the Earth, not everything in the heavens is perfect, there's a lot of cracks begin to appear in this Aristotle model. But the final thing that Galileo did to sort of dispel this Ptolemaic model had to do with observing Venus. And this is something someone mentioned in the beginning of class. We talk about it a little bit. Okay. So imagine you take the Ptolemaic model very, very seriously. Okay. Ptolemy says, look, the Earth is here, and Venus goes around the Earth on a circle. A loop-de-loop, like this. Okay. And it's known that Venus always appears on the horizon or in the sky very close to where the sun is. You only ever see Venus sundown or sunup. It's always hanging out near the sun. Okay? And why is that for real? We know why that is. Who knows why that is? Why is Venus always near the sun in the sky? Because it's closer. It's very close to the sun. It's very close to the sun. It's going around the sun like this. So from our vantage point, it's always kind of in the same area in the sky as the sun. Okay. But it was known. I mean, it's just a fact. Okay, that's where Venus is. And Ptolemaic model had that built in. Okay. So in the Ptolemaic model, it turns out the center of Venus's epicycle, okay, the center of this loop-de-loop that it does, always tracks the sun. You have to do that in order to get it right. This was built into the model. So now, okay, what I'm doing is I'm getting very precise. This is how you kill scientific theories. This is really all the scientific method can do is kill theories. You can never rule anything in. You can only rule stuff out. Okay? If you want to rule stuff out, you got to take it very seriously and see, all right, well, if I take this model seriously, what should I see in the sky? If you think about this, what this means is that the light from the sun should never be fully lighting up Venus in this picture, because Venus is always kind of hanging out right around where the sun is. So it's never over here. Okay, the sun is never here, and Venus, Venus is never here when the sun is here. So it's not like the sun is ever fully lighting up Venus, and you can see a full moonish type Venus. You can never see a fully lit up Venus. You should only ever see a crescent Venus in this picture. Does that make sense? It's like a tennis ball very close to a light bulb. You never would light up the full tennis ball, you only light up one edge of it. So it would look like a crescent. And Galileo understood this. Now, of course, in the Copernican model, or Kepler's model, Venus goes around the sun. So sometimes, relative to where the Earth is, Venus is fully lit up by the sun. You ought to see it as a circle on the sky. Sometimes it's only half lit up by the sun, and sometimes it's not lit up by the sun at all from your viewing point. So it ought to go through phases, just like the moon goes through phases. Does that make sense? So Galileo understood this. He said, oh, okay. Now the problem is, in the past, Venus was just like a bright thing in the sky. It just looked like a dot, because your eye cannot resolve any detail. But with a telescope, suddenly it comes into sharp view. And you begin to make out the difference between something that's just like a blob of light and something that actually looks like a crescent or not. Okay? So that's what he did. He was able to use his telescope and look to see whether he saw the heliocentric prediction or the Ptolemaic prediction. And what he saw was the heliocentric prediction. Okay? Which means he rules this one out. The universe does not look like this. But it does look like this. So that doesn't mean that this model is right. There might be something else wrong with it. But it does mean that this model is wrong. And you're done. And you can dismiss this model and you never have to talk about it again. This is really what the scientific method is. This is, people have ideas for how things ought to work. But in the context of this model that you have for how the universe works, you have predictions. And if you are able to do an observation that rules it out, you throw that model out and you never talk about it again. And all the models that live on live to play another day and survive another test. And the models that we really believe now, the ones that are called theories now, that are sort of theory with a capital T, are ones that have survived a very large amount of testing like this. So every astronomer today wants to be Galileo. Okay? They all want to kill some model. And the bigger the model, the more entrenched the model, the more famous you get for killing it. Okay? If I could kill general relativity, that would be very good. You know what I mean? If I was a biologist and I could kill the theory of evolution, I would be a very famous biologist and very rich. Okay? There's a lot of incentive to kill theories because that's all we can do. And the ones that survive the most tests are the ones that you believe, you begin to believe. So we're running out of time. We've got a little bit more time. So what I want to do at the end of lecture here is to go back to Kepler's laws. Before I do that, does anyone have any questions about the stuff I've talked about with Galileo? Do you understand what I was saying with the Venus phases and all this stuff? Okay. There's some other, pretty interesting stuff that Kepler was able to deduce by studying all this data that had been collected on the planet. And while what Galileo did was very, very impressive in terms of doing experiments, and Galileo did a lot of other things as well for science. I may talk about it a little bit. Kepler was one of the first people to really take empirical data and try to describe it in a complete way mathematically, which brought precision to science in a way that probably wouldn't be overcome until Newton really brought the full force of mathematics to usher in the modern scientific age. And so in order to talk about what Kepler did, I have to talk a little bit of mathematics, not too much, but I think it's a useful place to begin. So here are Kepler's 3 laws, and I'll talk about them each in detail, but just to state them. Okay, planets orbit the sun in ellipses. Okay, we talked about that already. And the other thing that they do is they sweep out equal areas in equal times. And I know that doesn't make any sense until I talk about it. But basically what this says, with somewhat more precise form, is that if a planet is going around the sun in an ellipse, it goes faster when it's closer to the sun, and it goes slower when it's far away from the sun. So like when it gets near the sun, it speeds up, and then it slows down, and then it speeds up, and then it slows down. So that's basically what the second law is. It's something like this. Okay. Now, he didn't know why, but he just said, if I look at all the data, this is what's happening. And there's a more precise way of stating this result I'll mention in a second. And the third is, and this is the most mathematically complicated thing that he says, is that if you take the period of the planet's orbit around the sun, what is a period? Who knows what's a period of an orbit mean? What does that mean? Someone must know. Yes? Yeah.
Time frame?
Yeah, the time. So what's the period of the Earth's orbit around the sun? Does anyone know? Yeah, a year. All right? So the period of the Earth's orbit around the sun is a year. So that's what the period is. It's just how long it takes for it to go around the sun. Okay. the first thing he said was, in broad sense, he said that the bigger the period of the orbit, the farther the planet is from the sun. So r here is supposed to mean the distance from the planet to the sun, and p is the period. Okay. So the first order thing he said is that the farther planets are from the sun, the longer it takes them to go around. All right. But it's a more precise relationship than that. What he said was that the square of the period is proportional to the distance to that planet cubed. Okay? So this funny symbol right here means proportional to. Who has seen this symbol before? I just wonder. Okay, about half. So there's probably another half of you who are like, what the hell? Okay. This is kind of like an equal sign. All right? Except if it were an equal sign, I would have to put funny constants here. Okay, so it might be like, the planet period equals, the planet's period squared equals this distance from the sun cubed times some complicated number that has units and stuff like that. Okay, this takes away all the other multiplication and stuff. It just says proportional to. It's almost like a fractional relationship. I'll talk about that before, but it's actually even simpler than an equal sign, as you'll see. What this really says is if the planet's period is twice as long, okay, then the distance from the sun can be calculated exactly compared to the Earth. So the first one is, we've talked about this already, planets orbit the sun along ellipses. The sun sits at one foci, and the other focus is empty. It doesn't really mean anything. There's no magic anything going on at the other foci, really. It's just a mathematical thing. And the planet goes around on an ellipse. Eccentricities of ellipses, I just thought I would mention, is a way to characterize how much of a circle the ellipse is. Okay, so things that have very big eccentricities means it's less of a circle. And so this is just a definition that you're free to look at. But really what I wanted to show was this one here. If you look at this movie, what's going on is this is a small eccentricity, and then it gets bigger. So you can see how the orbit becomes more squashed as the eccentricity gets bigger. And it becomes more round, like a circle, and the eccentricity is small. The Earth's eccentricity is very, very small. So the Earth's eccentricity is like 0.01. So it's almost a perfect circle. The most eccentric orbit, except for Pluto, which we don't talk about anymore, is Mercury, which has an eccentricity of 0.25, which is even the most circular thing here. It's even slightly more circular than that. So this is just to keep in mind that although they are moving on ellipses, the ellipses are not like super elongated. They're almost circles. So if you want to have a picture in your head, thinking about the planets going around on circles isn't that bad. It's a pretty good approximation to what it really is. Now, the second law is the one that's maybe intuitively harder to understand at first. But this is what it says. It says that, let's say, watch this planet going around the sun here. And let's say I make a dot every, 3 months. Okay, so every 3 months, the planet moves a little bit farther around the sun. And I'm going to make a dot every 3 months. This is what it would look like. So out here, far away from the sun, the dots are very close together, but that's because the planet's not moving very fast. And as it approaches the sun, dots start getting farther apart because it moves farther in 3 months than it did out here. Okay, that's what's going on. The equal areas and equal times means that if I figure out what the area that is swept out between the point on the orbit, the next point on the orbit, and the sun in this time frame, this solid angle here, that's equal to any other angular pi that is swept out in that same time period. Okay? So it means the area of this triangle is the same as the area of that triangle. So it's the same thing here. The same amount of time, it takes the same amount of time to go from here to here as it does to go from here to here. And the areas of these triangles swept to the sun are the same. And that's a precise way of characterizing exactly how much faster stuff is going when it's closer to the sun compared to when it's farther away from the sun. Yeah?
Why is the sun centered in gravity?
Well, it's kind of complicated, so it does have to do with gravity, yes. And I won't be able to actually explain to you exactly why the sun is right at the center of the ellipse. But it turns out that if you solve the full equations that were derived by Newton to explain gravity, that there's only one way that you can have a planet orbiting something like the sun and have that orbit be stable. That is, have the orbit continue on forever. And that is to have the sun at the foci of an ellipse where the orbit is on an ellipse. And if you tried to, for example, the planet's moving here, and you tried to just if you just move the sun a little bit, the sun would still be tugging on the planet. The planet would then still get pulled towards the sun, but then it would fly off in some arbitrary direction, and the orbit would keep doing that forever. So it turns out that unless you put the sun right on the focus of an ellipse, the orbit would decay very quickly and the planets go flying off. So it's sort of like a selection effect. You can envision an initial scenario. I mean, this isn't how we think planets exactly form, but you can envision a scenario where there are initially 100 planets going around the sun. But, 91 of them, or 92 of them, were not going around in such a way that the sun was at the focus of their ellipse. And those planets would just fly off and not keep going around for billions of years. So this is the most stable configuration you can have in something that's two things that are attracting each other by gravity. And that was something that Newton showed in about 200 years, which was really impressive. I mean, Newton, pretty impressive. And it turns out that the laws of gravity explain exactly why all this stuff is happening. Okay. That's a great question, by the way. So now, here's the third law. Here's Kepler's third law. And I wanted to give you an example about how you actually go about using it. And then this is the kind of thing that your TA is going to talk about next lecture, the next discussion section. If you have some trouble with this, you should be able to do these kinds of problems. So here's an example of how you use Kepler's third law. So notice I have that proportional sign. A simpler way, maybe, of writing Kepler's third law is like this. Okay? It's that if you take the period of a planet, whatever planet you're talking about, and you square it, and you divide by the period of the Earth going around the sun, which is 1 year, okay, and square it, that's equal to the semi-major axis of that planet, that is roughly the distance to that planet cubed, divided by the distance between the Earth and the sun cubed. That's what this is. So this is Kepler's third law. So it's a little bit mathematical in the sense that if you're not used to seeing these symbols, it might be a little bit intimidating. But what you'll see is, as you work this out on your homework, it's it's really not that complicated once you go through the steps. You just got to be meticulous about how you write things down. Okay. So for example, the period of the Earth is 1 year, okay? And the distance between the Earth and the sun is some distance in meters, but we call that distance an astronomical unit. Okay, that's how an astronomical unit is defined. Okay, so the period of the Earth is a year, and the distance to the Earth is an astronomical unit. So those are very simple numbers. The period of Jupiter, okay, which we can measure, for example, is 11.85 years. So Jupiter takes 11, almost 12 years to go around the sun. But from this, we can figure out what the distance to Jupiter is. Okay? Because we know the period of Jupiter divided by a year, which is the period of the Earth, squared, is equal to distance to Jupiter divided by an AU cubed. This is Kepler's third law. So we solve this equation. Okay? Now we know that the period of Jupiter is 11.85 years. We stick that in. And we're solving for r. So it says 11.85 squared is equal to r in units of astronomical units cubed. So 11.85 squared is 140.4. Okay? I take the 1/3 power of each side to get rid of the 3 here. So then I have 140.4 to the 1/3. This is equal to the radius of Jupiter in AU. And if you take the cubed root of 140.4 with your calculator, you'll find it's 5.2. So what this says is that Jupiter is about 5 times as far away from the sun as the Earth is.